Good morning, Amherst. Today we will be focusing on worksheet 6, the hydrolysis of salts. There's some pretty good stuff in your note packet on this as well, too, for examples. It's a little backwards, but if you look in the examples, in the notes, it'll give you some pretty good in-depth information about what's going on, because hydrolysis is a little counterintuitive. But here goes nothing. All right, let me get a sheet of paper here. So literally the term hydrolysis comes from hydro, meaning water, and lysis, to split. So we're talking about breaking water apart into hydrogen ions and hydroxide ions, at least under one conceptual definition. Splitting water apart. So you can think of it in terms of reverse neutralization. If neutralization is acid plus base will give you salt plus water. If I put a salt into water, shouldn't I get acid plus base? Well, if that's the case, we know that some acids are stronger than others and some bases are stronger than others. In which case, your resulting solution might turn out to be acidic, basic, meaning alkaline, or neutral. So it depends on what salt you put into water. Now, the key to remember is that the strong acids and the strong bases, they do not hydrolyze. They like to dissolve in water. The acids completely ionize, the bases completely dissociate, and they don't want to break apart water. They like being dissolved in water, if you will. It's the weak ones you need to look out for. Sneaky weak acids or bases will turn around and break water apart to find the ion from water, if you will, that will help them neutralize. So here's a salt, XY. You're going to do a double replacement reaction with water, HOH. And you're going to get XOH, that's the base, and HY, that's the acid. Okay? And you could have strong or weak on either. You just do a double replacement with water. Well, if you look at this, there are 4 possible combinations here. You could have strong with strong. You could have, that would be strong and strong this way. You could have weak and weak this way. You could have strong and weak this way, or you could have strong and weak that way. There are 4 possible combinations here. So if you take a strong acid with a strong base, neither is going to break apart water. They're not going to hydrolyze. You're going to end up with a neutral solution. It's going to be pH 7. If you take a strong acid with a weak base, the acid's going to win. It seems like, pretty simple. Your pH is going to be less than 7, but it's not because of the acid. It's actually because of the base. I'll explain that in a minute. Weak acid, strong base, well, the base is going to win. You're going to have an alkaline solution. The pH is going to be greater than 7. You think it's because of the base, but it's actually because of the acid. And if you have weak and weak, you can't really tell without more information. Weak and weak, which one's weaker than the other? Is that the same way as saying which one's stronger than the other? It's not the same definition as strong and weak. It's stronger and weaker. Kind of goes back to that conjugate acid base Bronsted-Lowry thing we were talking about. If you've got 2 weak species here, one is weaker than the other, which means one is stronger than the other. So in this case, you've got a rather uncertain situation. You would need more information to make any kind of prediction about the resulting pH of the solution. Just remember, the terms strong and weak are not the same as stronger and weaker. The strong acids were the top 5 from your supplemental table. HI, HBr, HCl, HNO3, and H2SO4. They've got 100% ionization in water. There is no reverse reaction. They go forward and they stay that way. They won't break water apart and go back the other way. Strong bases are the group 1 hydroxides and the lower group 2 hydroxides. And don't forget, ammonium hydroxide and calcium kind of splits the difference. We'll stay away from calcium because it's right in the middle. So lithium, sodium, potassium, rubidium, cesium, and francium with hydroxide. Strontium, barium, and radium with hydroxide taken twice because of group 2. 100% dissociation in water, no reverse reaction. Now, realistically, we're probably not going to deal with cesium, francium, or radium because, they're radioactive, and their radioactive properties would kind of supersede their chemical properties. So we'll avoid those as well. Let's go through some examples. First example, let's just do plain old table salt, NaCl. So in NaCl, I've got Na positive and Cl minus in water. You can think of it as HOH, H positive, and OH minus. Do a double replacement here. What are you going to get? You're going to get HCl and NaOH. Well, HCl, that's top 5. that's strong acid. NaOH, that's group 1 hydroxide, that's strong base. You're going to get a neutral solution. Pretty easy to predict there. Strong and strong will give you neutral. But why? Well, sodium will not break apart water. Water is its friend. It will not split water apart. No reaction there. Chloride will not break apart water. Chloride likes water, likes to dissolve in water, is not going to do a reverse reaction. HCl goes forward 100%. NaOH goes forward 100%. There is no reverse reaction. No hydrolysis. Strong acids and strong bases do not hydrolyze. If it's strong and strong, you get a neutral solution. All right, example number 2. What if we had something like magnesium nitrate? MgNO3 taken twice. So it's Mg plus 2, NO3 minus, H positive, OH minus. Do your crisscross, double cross, applesauce. HNO3, that's top 5, that's a strong acid. MgOH twice, well, it's group 2, but that's not the lower group 2, that's the top half of group 2, so that's going to be a weak base. Strong acid, weak base, well, pretty straightforward. You say the acid wins, yes. Your solution is going to be acidic with a pH less than 7. But why, Santa? Why? Said little Cindy Lou Who. Well, the NO3 will not hydrolyze. The ion from the strong acid will have no reverse reaction. It's not going to react. It's not going to break apart water. It will not hydrolyze, will not split water. However, magnesium at plus 2 is not as friendly toward water. Magnesium would like to be not dissolved in water and basically says, hey, water, looks to me like you're made up of H positive and OH minus if I were to split you. And I'm positive too. I'm looking to get some negative to get out of here. So this magnesium splits part 1 water, takes the hydrogen from it. Takes the hydroxide from it, takes the negative. The positive is looking for the negative. So you have MgOH positive, leaves that H positive in solution. Now this is not quite done yet. It is the principal hydrolysis reaction, but in order to get back to neutral, this MgOH positive has to break apart a second water, and it's going to do that off with his head. It's going to grab the other hydroxide, leaving another additional H positive in solution. Now these are not 100%, these are equilibria, okay? Some of these are going to go forward, and some are going to go backwards, and some of these are going to go forward, and some of these are going to go backward. That's fine. But in any event, you're creating some hydrogen ions here and some hydrogen ions here, and those are left in solution, and that's going to drive your pH down, and you're going to end up with an acidic solution. Not because of the acid, but because of the weak base. The hydrolysis reactions here, the splitting of water, in order to get back to undissolved compound here, results in leaving excess hydrogen ions in solution, which came from the water molecules that were, had their heads chopped off. Example number 3, what if you've got a weak acid and a strong base? Well, right off the bat, the strong base is going to win. You're going to have an alkaline solution with a pH greater than 7. Here's my example, lithium fluoride. Lithium is plus 1, fluoride is negative 1, H positive, OH minus. Crisscross double replacement, you're going to get HF and LiOH. HF does not make the top 5. That's a weak acid. LiOH, that is group 1, that's a strong base. The base is going to win. This is an alkaline solution with a pH greater than 7. But why, Santa? Why? Little Cindy Lou Who says, well, the strong base will not hydrolyze. Water is my friend. I wouldn't dream of harming a hair on your head. Leave water alone. No reaction there. Fluoride is not such a nice player in the game. Fluoride says, hey, water, how's it going? Off with his head. Chop that water apart. I'm interested in the H positive, not so much the OH minus. So it takes the H positive and leaves the OH minus behind in solution, which drives your pH up. This hydrolysis reaction, it's going to have an equilibrium, but it's going to create some hydroxide ions, which will make the pH greater than 7. And finally, what if you have weak and weak? The temptation is to say, well, it's going to be neutral again. It's not going to be neutral again because one is weaker than the other. So, for example, if I had iron 2 sulfite, ferrous sulfite, Fe plus 2 and SO3 negative 2, H positive, OH minus, do the double replacement thing. You're going to get H2SO3, that is not top 5, that's a weak acid. You're going to get FeOH taken twice, that is not group 1 or group 2, that's a weak base. Weak and weak. You're going to need a lot more information to figure out the pH of this solution because it depends on the relative strength of these. which one is weaker than the other? To what extent does each one hydrolyze? And you could take AP chemistry and study some KEQ values for that and figure it out. But basically, here's how it goes. Your iron plus 2 is going to break apart this water. Off with his head. I'm interested in your hydroxide. Leave the... H positive, OH minus. It's interested in hydroxide. Leave the H positive behind. Same thing here. FeOH positive is interested in the additional OH. Leave the H positive behind. I would apparently have written this backwards. It's all right. So it's stealing the hydroxides and it is leaving the hydrogens in solution. So over here, this one is interested, consistently leaving things backwards behind. You get the point though, these are going to be OH minuses. SO3 negative 2 is going to break apart the water. It's interested in the H positive, takes the H positive, leaves the OH minus behind. HSO3 minus is also interested in the H positive, leaves the OH minus behind. So these would want to drive the pH down, these would want to drive the pH up, and it depends on the K values for each of these. So let me move this over so you can see a little bit. Depending on the KEQ values, there may be more hydrogens or there may be more hydroxides or vice versa. Your answer is, I don't know what the pH of this solution is going to be. I need to take AP chemistry and talk to Mr. Bauer about that. In any event, if you have weak and weak, you say pH unknown. That would answer things for us at this point in time. All right, so your homework. You're going to go to worksheet 6. Now to answer worksheet 6 is pretty straightforward because it's just asking you to predict acid, basic, or neutral. And there are 13 problems there. However, you're going to need to be able to write hydrolysis reactions. So I would like you to practice writing the hydrolysis reactions because coming up to a homework assignment near you this week and a test, you will notice, for example, this is your practice test number 52, is it's going to ask you to write the hydrolysis reactions or lack thereof. So you need to be able to do all this crazy, does it hydrolyze or not? You need to be able to do these. All right, so that's your homework for tonight. I will post a key with extensive reactions tomorrow morning. We are going to test out this week of this unit. That is the last new material for this unit. So if you look at acids and bases, we've gotten through everything now. Coming up, if you want to get started early, we'll have Regents Review. I'll make a Google Forms out of that somehow. And then we'll have a practice test, and I'll make a Google Forms out of that somehow. And then we'll do a test, and I'll make a Google Forms out of that somehow. And we should be out of this unit by Thursday, Friday at the latest. Redox and electrochemistry next. Take care.